Welcome to the first substantive lecture of the short semester that covers the basics of social scientific research. In this lecture, we will be discussing what constitutes social science by walking through the research stages and thinking carefully about research design used to establish causality. I expect that there's variation in how much students in our class know about statistics and methodology. So for some of you, this lecture might serve as a refresher, and for others of you, this might be new information on the terms and concepts utilized in social scientific research. In any case, we're kicking off the semester with a pretty hefty lecture. It's quite long, and there are a lot of terms and concepts, so it is definitely not the most fun that we will cover in the class this semester. In fact, this is probably my least favorite. No, it is definitely my least favorite of all the things that we will discuss. But since you'll be reading and analyzing a lot of social science research, not only in this class, but in other political science classes, this introductory lecture will provide us with a really solid foundation going forward. So even if this isn't your cup of tea, don't give up. I promise the next lectures will be far more entertaining and engaging. There are 4 central questions that motivate this lecture. What is social scientific research exactly? Why is it important? Why should we care? More importantly, for our purposes, what can social science tell us about the judiciary? That's what we're going to aim to answer this entire semester. And fourth and finally, once we've established that social science is awesome, we need to recognize that it has its limitations. So what are the limits to social scientific research? This class serves 2 purposes: description and argumentation. Description provides the skeletal knowledge about the judiciary, or the basic facts about the court. So, for example, together, the United States Constitution and the U.S. Code inform us about the staffing of the court. We know descriptively that there are currently 9 seats on the Supreme Court. But that basic descriptive fact doesn't tell us very much about the court, about the 9 justices who sit on the bench, or about the process by which they got there. We know, too, that federal judges and Supreme Court justices get to keep their jobs, provided they don't screw up too egregiously. But this descriptive fact also doesn't tell us a whole lot. It doesn't tell us, for example, when or why judges and justices would ever leave their jobs. So these types of facts raise puzzles, and argumentation is born from questions that are derived from seeking to flesh out that factual skeleton. We can observe variation in what happens with this descriptive element when we consider how the justices get onto the court in the first place. So, for example, we know that some nominees make the president's shortlist and some do not. Some nominations get confirmed unanimously by the Senate, and some do not. This observed variation leads us to question the underlying process. In particular, what leads the president to pick one nominee over the other? Why do some senators vote for confirmation while others try to block the nominee? The point of emphasis here is that these are empirical questions, which means we can bring quantitative data to try to answer the questions. There are tens of thousands more empirical questions, not just about the court, but about everyday life, that are just floating around in the world waiting for answers. Social scientists of all stripes, political scientists, economists, sociologists, psychologists, make their living by uncovering and trying to answer these types of questions. We're going to spend some time walking through the 6 steps of social science research: question, theory, measurement, analysis, conclusion, and then the ever-iterative repeat process. The very first step of the process is to propose a research question. This sounds entirely simple, right? But where do research questions come from? There are questions everywhere. If you look around the social, political, economic world, you'll observe a lot of variation, and a curious researcher will puzzle about the cause of that variation. So we see variation in lots of things, but not all questions are equally important. It's a good idea to think about the so what of the question. Why should we care about the answer to the question? If you can't convince anyone else that what you're asking is an important question, it's probably not worth the effort to spend time researching to find an answer. The very first step of the social science process leads to repetition, since trying to answer one question often begets another. This is how scholars build what is called a research agenda. Researchers are expected to have expertise in a related body of work, and much of it comes back to the types of questions we ask. Okay, so we know questions are everywhere, awaiting our observation, and that some questions are more important than others. Why people choose to vote for one candidate and not another is a good example of an important research question, and it's an example that we'll weave throughout the class today. Before you move on, stop for a moment and think about how you would answer this question. Why do you choose to vote for a political candidate and not someone else? Why does it matter? Social scientists and the mass public care about this because elections are a ubiquitous aspect of life in a representative democracy, and politicians care because the answer to this question will provide them with useful information as they try to win election. The next step of the process is to theorize. In other words, what are the potential answers to your question? A theory is a formal statement that classifies processes or actions, predicts future events, explains past events, aids causal understanding, and guides research. In short, a theory allows us to generate hypotheses about possible answers to our questions. So, for example, rational choice theory, which has its origins in economics, says that when faced with two or more choices, people will always pick the one that yields the most utility. Utility is a catch-all term for an overall benefit, for money, for happiness, and the like. So in our working example, when we want to know why an individual votes for one candidate and not another, rational choice theory would tell us that a person picks the candidate that gives them more utility. Equipped with a theoretical framework, we then derive a hypothesis, which again is a statement derived from your theory that is assuming that your theory is accurate. This is something we can observe when we're answering the research question. Put in more concrete terms, people get utility from having policies enacted that they like. Therefore, they will choose the candidate whose policy preferences are closest to their own. Or stated more formally, as what we call a testable hypothesis, as the ideological distance between a voter and a candidate decreases, she will be more likely to vote for that candidate. This is something that we can measure, that we can test, that we can quantify, and that's the goal, right? We want to find ways to put our theory into practice by generating testable hypotheses. Now that we're equipped with our question and a theory about how to answer that question, we need to identify the variables of interest. A variable is an empirical measurement of a characteristic that varies, which means that it takes on more than one value among subjects in a sample or population. There are lots of examples: an individual's sex or gender as male or female, that person's school class as a freshman, sophomore, junior, senior, first, second, third, fourth, fifth year, super senior, a person's age, 0, 1, up to 100, someone's interest in politics on a scale from 0 to 100, or in a smaller scale from low, medium to high. There are lots of different ways to classify variables. If a variable is quantitative, then it means that it is measured on a numerical scale. So age from birth to death counts up and is always a numerical value. Many variables, in fact most variables in social science, are categorical, which means that even if we assign them numbers, it's measured on a non-numerical scale. So from our previous example, this includes things like gender or interest in politics. We can further subcategorize categorical variables by type. Nominal categorical variables are things where the value of the characteristic is unordered. So, for example, while we might code sex or gender in our study as 0 for male and 1 for female, these numbers don't mean anything. While in a numerical sense, 1 is greater than 0, in a categorical sense, 1 is not greater than 0. Females are not greater than males. Conversely, ordinal categorical variables are those in which values have a natural ordering and actually mean something, like ranking interest in politics from low to medium to high, where if we coded those, if we categorized them as low as 0, medium as 1, 2 is high, though that order means something. Those numbers carry value even if they are not the same sort of quantitative numerical measurement like age. I'd like you to take a few moments now to pause the lecture and try to classify these variables. Literally push pause. Take some notes. So how would you classify marital status, income, pet ownership, party affiliation, political ideology? As you're working, keep in mind that if you think it's a categorical variable, you should also identify if it's a nominal or ordinal variable. Okay, did you pause the lecture? I hope so. If you haven't, finish working and push play when you're ready. But now let's go through those together. If you guessed that marital status is a nominal categorical variable, you'd be correct. Income could be either quantitative or categorical, depending on how we measure it. If we measure it from, say, 0 to infinite dollars, that's an integer value, and integer values are quantitative. But if we divide income into brackets, say less than $25,000, $25,000 to $49,000, $50,000 to $74,000, and more than $75,000, then we'd classify that as an ordinal categorical variable because you can't just subtract one category from another, right? Does that make sense? Like marital status, pet ownership, and party affiliation are nominal categorical variables, and political ideology is like income in that we could measure it quantitatively if we use a large numerical scale, or it could be an ordinal categorical variable if we measure it on a 7-point scale from left to right, for example. There are two more types of variables that are probably more important for our purposes this semester. The dependent variable is the variable whose initial variation motivated our research question, while the independent variable or variables are the things that we identify as being related to the dependent variable when they came up in our theory or hypothesis. In other words, the value of the dependent variable depends upon the value of the independent variable. That is, we expect that if we change the value of the independent variable, the dependent variable will change because of it. Let's return to our example for a moment. As the ideological distance between a voter and a candidate decreases, she'll be more likely to vote for that candidate. What was our initial question again? We want to understand how likely a person is to vote for a particular candidate. So that, the likelihood of voting for a candidate, is our dependent variable. And we're hypothesizing that this depends on how ideologically proximate the voter is from the candidate. So ideological distance is our independent variable. If we increase or decrease that distance, then we expect that the likelihood of voting for a particular candidate will increase or decrease accordingly. All right, I'm going to read you a few statements, and I want you to, again, pause the video and take time to identify the dependent and independent variables in the following 5 examples. If states restrict abortion rights, the number of abortions will decrease. Women are more likely than men to favor environmental regulation. If a person is a strong political partisan, the likelihood that she will campaign for her party's candidate will increase. Crime rates are higher in states with strict gun laws than in states without strict gun control laws. The lower the education level, the higher the odds of smoking. Seriously, pause the video and come back. Are you finished? Did you pause it? All right, let's walk through this together. In the first hypothesis, we observed variation in the number of abortions in states. So that's our dependent variable. We think this depends on the number of restrictions or laws in a given state. So that's the independent variable. In the next sentence, we argue that women are more likely to favor environmental regulation. So again, we observe differences in the favorability of environmental regulation. And we think this depends on gender, our independent variable. In the third example, we're looking at variation in the likelihood that a person campaigns, which is our dependent variable. We theorize that this depends on partisan strength, our independent variable. In the fourth example, you'll see variation in the structure of the hypothesis. Here, crime rate is our dependent variable. It's listed first. And we think that that depends on the strictness of a state's gun control laws, which again is our independent variable. In the final example, we're motivated to discover what affects the odds of smoking, our dependent variable, and we argue that this is affected by education level, our IV, or independent variable of interest. Once we have our hypotheses and identify the variables of interest, the challenge is figuring out how to measure concepts, which is called operationalization. In our example, candidate vote choice is the dependent variable. This is pretty easy to measure, though we could measure it in different ways. We could identify whether the candidate is a Democrat or a Republican, whether the candidate is the incumbent or the challenger, or whatever the candidate is or whether the candidate is a minority or a non-minority, for example. However we operationalize this, it's a straightforward classification. But measuring our independent variable, the ideological distance between a voter and candidate, is much, much harder. In a perfect world, we would have a very precise value for both candidate and voter on the same scale, like from negative 100 to positive 100, from left to right. We could just subtract the distance and get a very precise measurement. But it's not clear how to put individuals and candidates on the same scale. We could try to implement a survey to question both the voter and the candidate, but this would be both really time-consuming and expensive. So instead, we need to use a proxy or a substitute measurement. In this case, partisan affiliation is plausibly related to one's ideology and is relatively easy to obtain. So in practice, this means that we could measure the independent variable as whether or not there is partisan agreement between the candidate and the voter. If there is agreement, let's code this as 1. If there isn't agreement, let's code that as 0. So in our hypothetical research project, this means that if the voter and candidate are both Democrats or both Republicans, they're coded as 1, and if the voter is a Democrat and the candidate is a Republican, or the voter is a Republican and the candidate is a Democrat, then we have a mismatch and we code this as 0. Does that make sense? What type of variable would our independent variable be as a result? If you guessed nominal categorical variable, you would be right. There are a few more things we need to consider before we put step 3 of the research process to bed. We've got to figure out how to evaluate our variables. There are 2 key concepts we use to determine whether a variable is a good one: reliability and validity. A reliable variable means that the measurement procedure yields consistent results. Like, say, if you step on a scale, step off, and step back on, if you get the same value over and over again, it's reliable. A valid variable, on the other hand, means that the measurement procedure is only related to the main concept of interest. So this means that when you step on a scale, it reads your actual weight. Both reliability and validity are necessary to make a variable a good one, but reliability is usually a whole lot easier to establish than validity. Let's look at a concrete example to see why that's the case. Let's say we'd like to know whether or not it's cold in East Lansing. I'll propose that to answer this question, we define a day as being cold if and only if, at some point during the day, the raw air temperature as measured at the Lansing airport went below 32 degrees Fahrenheit. Is this a reliable procedure? Sure it is. With these specific instructions, anyone could conduct the same process, and we could repeat this with consistent results. But what about the variable's validity? That is, does the goal match with the measurement procedure? Unfortunately, probably not. Simply measuring whether or not the raw air temperature ever hits 32 degrees or below doesn't take into account other things that impact feelings of coldness, like wind chill, how much time of the day is below 32 degrees, whether the sun is out. It's a very coarse measure. To this point, we have a question, we have expectations about possible answers, we know what variables we need to collect, and now we need to do the actual research. The goal of analysis is to establish causal relationships between independent variables and the dependent variable, where some change in the IV causes change in the DV. There are 4 big hurdles to establishing causality. First, we need to know if there's a credible causal connection between the independent variable and the dependent variable. Then we need to consider whether the DV could actually cause the IV, which is something known as reverse causality. If there's a relationship between the IV and the DV, we need to know whether that relationship is meaningful or statistically significant. In other words, is there systematic covariation between the IV and the DV that we wouldn't see by chance? And even if there is a statistically significant relationship, we need to consider the possibility that the relationship is spurious. Spuriousness occurs when a third variable actually causes both the independent and dependent variable, which makes us erroneously believe that the IV and the DV have a causal relationship. Let's take a true statistically significant correlation. We see that when ice cream consumption goes up, so too does the number of drownings. As a result, we might conclude that we need a policy to ban ice cream. This is absolutely silly, right? It's a funny example. So let's check for spuriousness. Is there another variable that would cause both ice cream consumption and the number of drownings to go up? Of course there is, right? Outdoor air temperature. As the temperature goes up, more people eat ice cream and more people go swimming, which will increase accidental drownings. In short, once we account for the effect of heat, the apparent relationship between ice cream and drowning completely disappears. As we're doing the actual research to answer our question, we need data. There are 2 types of data that we can gather: observational and experimental. Observational data are those that exist naturally in the real world, even if they haven't been formally recorded yet. These data can be prospective, that is, that they can exist in the future, or they can be retrospective, like we can go back into the archives and mine for historical data. But it always means that the researcher observes something that naturally occurs and then records the values of the IV and the DV and then does some statistical analysis to examine covariation. We're going to go through a few examples of possible research questions and figure out how we'd study this using observational data, and then we'll use the same examples to consider how we'd study the question using experimental data. So first, let's say we want to know whether the amount of sleep you get influences your performance in college. Hopefully by now you recognize that the amount of sleep is the independent variable and college performance is the dependent variable. Our theory is that sleep is the key to being alert and to the process of learning, and that the lack of sleep leads to poor academic performance. Side note, this is absolutely true. Okay, so we've got our theory, we have our hypothesis, and now we need to figure out how we're going to measure this. One measurement procedure could be to conduct a multi-wave survey of college students, asking students at 5 points during the semester how many hours they slept the previous night and the night before. That's our independent variable. At the end of the semester, we could ask them to report their semester GPA, our dependent variable. That's pretty good, right? But you should already be thinking about the quality of our variables. Are they reliable? Are they valid? For example, does the quality of sleep matter? Or is it simply the time that a student spends in bed? Returning to our earlier example, our research question wondered if ideological distance between an individual and a candidate impact an individual's voting behavior. We'll use our theory of rational choice policy utility argument to generate a hypothesis and then measure it by conducting a survey to ask people their party affiliation and who they voted for in the last election. Remember that the IV is whether the party affiliation of the voter and the candidate match if they're the same during the last congressional election. The dependent variable is whether the voter chose that candidate. Again, what might be some of the problems with reliability and validity? Some potential considerations might be the trustworthiness of our participants' responses, that is, some people might lie about their voting history, or perhaps a voter changes their party affiliation. All right, let's do one more example for good measure. Let's say our research question is, does taking a small dosage of aspirin reduce the likelihood of having a heart attack or stroke among adults over the age of 50? We theorize that aspirin thins your blood, which lowers the risk of clotting, which causes heart attacks and strokes. Our measurement procedure will once again be a survey. This time we'll ask people if they are currently on a low dosage aspirin therapy or not. That's our independent variable. And we'll ask whether they've had a heart attack or stroke in the last year. That's our dependent variable. This seems reasonable, but let's check for spuriousness. Is there a third variable that is likely related to whether someone decides to take aspirin therapy and whether they've had a heart attack or a stroke? I think the answer is probably yes. Someone's overall level of healthiness most likely causes both. Healthy people are probably more likely to be aware of the benefits of aspirin therapy and be doing it, and healthy people are also likely to eat better and exercise, which reduces the risk of heart attack and stroke. Okay, so potential spuriousness in example 3 raises a pretty big concern, right? Without accounting for overall health, we can't conclude that aspirin therapy alone causes a reduction in heart attacks and strokes. Let's go back and think about potential spuriousness in other examples. Is there a variable that likely affects sleep and also academic performance? Probably yes, right? Things like mental, emotional, physical health, drug problems, those sort of things probably both affect a student's sleep patterns and their performance in college. What about an example 2? Is there a variable that likely affects whether you have partisan agreement with a candidate and also affects whether you vote for that candidate? This one's harder, right? I can't really think of anything that would cause both the independent and dependent variables in this case, so I'm going to conclude that spuriousness is probably not a huge concern here. But spuriousness is always a potential concern when dealing with observational data. To solve it, the researcher must be able to identify and measure all potential variables that are related to both the independent and dependent variables. That's what it means to account for or control for other possible explanations. So later this semester, when we get into statistical models, and I will say that we accounted for or controlled for things, it's because we're trying to isolate the influence of the key independent variable in the explanation of what causes the change in the dependent variable. Experimental data seek to overcome the inherent problems with observational data. Experimental data are those that are generated by the researcher through an experiment, where he or she randomly manipulates levels of the independent variable and observes changes in the DV. The classical experiment is to assign subjects to either a treatment group, which receives a high value of the IV of interest, or assign them to a control group, which receives a low value of the IV of interest, or none at all. This is the gold standard in conducting research. Because of random assignment, it is impossible to have spurious relationships. In turn, this allows you to have very high confidence in the study results. Let's quickly go through the same 3 examples using the experimental approach. Recall example 1. Does the amount of sleep you get influence your performance in college? In an experimental approach, we could recruit a group of college students, put their names on a list, and for each person, flip a coin. If it comes up heads, assign them to the treatment group. If it's tails, assign them to the control group. Students in the treatment group are forced to stay up all night doing various activities, TV watching, reading, playing games. Students in the control group, on the other hand, are told to go to bed at 11 p.m. and wake up at 8 a.m. In the morning, both treatment and control groups take a series of tests that measure intelligence and problem-solving skills. Researchers then simply look to see if the average performance for the treatment group is different, it's probably lower than that of the control group. Think for a second about whether or not there's a potential issue with spuriousness here. Is there a variable that causes both the independent variable and dependent variable? If yes, and it's not accounted for, that's a problem. What are the IV and DV in the experimental version of example 1 again? Recall the IV is assignment to treatment or control group, and the DV is performance on some tests. So spurious check. Is there a variable that causes someone to be assigned to the treatment control that also affects how they perform on the tests? No. Assignment to the treatment or control group was done randomly by a coin toss, so there's no reason to think that anything that causes the coin to be heads or tails also affects test performance. But you might be wondering about other things that matter, like how about raw intelligence? Raw intelligence would certainly affect how you do on tests, right? Yep, you bet it would. But the coin doesn't know if you're smart or if you're dumb when it assigns you to the treatment or to the control group. In other words, there will be smart people in both the treatment group and the control group, and there will be dumb people in both groups too. As long as your groups are reasonably large, you will have a mixture of all characteristics in both the treatment and control group. The specific size of the sample depends on how rare or frequent the characteristic is in the underlying population. As it gets more rare, group sizes need to be larger to ensure variation in both control and treatment groups. The key attribute of an experiment is the random assignment of the levels of the independent variable that are done by the researcher. Our example was simple, sleep versus no sleep, but experiments can be more complicated too. We could determine that different students get different amounts of sleep. So the control group could get a full night of sleep, and then we could have 2 treatment groups, or one treatment group gets no sleep, and the other treatment group gets 4 hours of sleep. And we could randomly assign students to the control or treatment groups by a roll of a dice. Say 1 or 2, you wind up in the control group. 3 to 4, you get no sleep. 5 to 6, you get 4 hours of sleep. Or easier yet, we could use a computer. In short, though, even though experiments provide us with the gold standard in terms of randomization so that we get away from the spuriousness question, it doesn't necessarily mean that they're straightforward or simple. Sometimes they're tougher to implement, and they can have lots of layers of complexity. All right, let's skip ahead and take a look at example 3 next. Does taking a small dosage of aspirin reduce the likelihood of having a heart attack or stroke among adults over the age of 50? We could recruit a large number of people over the age of 50. We make a list of their names. For each person, flip a coin. If it's heads, we will assign them to take a small dosage of aspirin every day for a year. If it's tails, we assign them to take a small sugar pill, the placebo, every day for a year. At the end of the year, we can obtain medical records and see who had heart attacks or strokes and compare the rates for the 2 groups. Spuriousness check. Just like before, there's no reason to believe that anything exists that causes coin outcomes and also causes negative medical events. Random assignment means both aspirin and placebo group will have health nuts and very unhealthy people, men, women, etc. Now, let's take a step back and use an experimental approach to examine example 2. Does ideological distance between an individual and a candidate impact that individual's voting behavior? This is more difficult but still doable. We just need to get a little bit more creative. We could generate 3 fake candidate biographies or profiles where the fake candidate's ideology is at 0, 50, and 100, with 0 being super liberal, 50 being exactly moderate, and 100 being super conservative. Then we could recruit a large number of college students and randomly assign them to read the profile of one of the 3 candidates. Ask the students questions to determine what their own individual ideological beliefs are on the same 0 to 100 scale. Finally, we would then ask how likely a student is to vote for an exposed candidate. A quick spuriousness check again reveals that there's no reason to believe that a third variable is related to the decision to vote for a fake candidate and what random candidate the student is assigned to. Random assignment means that spuriousness is never a concern for experiments. If we find a relationship, we can be very confident that that relationship is true. This is called internal validity. Experimental studies have high internal validity because of random assignment. Observational studies have lower internal validity because of the fear of spuriousness. But the problem with experiments is that sometimes we have to get creative to mirror a natural occurrence. And in being creative with our experiments, we sometimes step away from the real world. Example 1, the sleep study, and example 2, the ideological distance, are especially guilty of this. Both use only college students, for example. Example 2 uses fake candidates as opposed to real ones. Many real medical studies, like experiment 3, will go on to focus on one sex or a specific age group, often young people. That brings us to external validity. External validity is the extent to which results from a study are generalizable beyond the specific context in which the study was done. Experimental studies will often have problems with external validity, and these problems are typically bigger problems than for observational studies. So in short, there are costs and benefits to both approaches to analysis. We started with a question. This is where we, with help of statistics, actually answer it in step 5. If we observe a relationship between our independent variable and dependent variable. Now, what we want to know is whether or not that relationship means anything. Is it due to chance, or is there a systematic relationship? In other words, is that relationship statistically significant? We ask this question for whatever type of research we conduct, whether we're gathering observational or experimental data. To see what this looks like in practice, let's think again about flipping a coin. Is the coin in your pocket a fair coin? First, we have to determine what it means to be a fair coin. Let's say that after flipping the coin a large number of times, the ratio of heads to tails should be somewhere close to 50%. Okay, so now we need to define what close means, right? Because close could be kind of a slippery term, and we need to be precise. So let's say that we'll tolerate between 49 and 51% heads outcomes. If it falls within that window, then we'll conclude that the coin is fair. If it goes outside of that window, then we conclude that the coin is unfair. To determine the answer to our question, let's use this procedure. We'll flip a coin 10,000 times and write down the percentage of heads outcomes. This 10,000 coin flip is one trial, by the way. So we repeat this procedure for a large number of trials. We want this repetition because we might get inconsistent results. Look at the x-axis here. See the green vertical lines that correspond with 49 and 51%? Let's say any time that a trial falls in this window, we'll consider the coin to be a fair one. If it falls outside of those green lines, then we'll conclude that the coin is unfair. I did a computer simulation and conducted this test using a fair coin. Of my 500 trials, where again, every trial is made up of 10,000 coin flips, 478 of them landed on tails between 49 and 51% of the time. That's pretty good, right? But even using what I know is a fair coin, sometimes the frequency landed outside of bounds. 11 times I had fewer than 49 tails, and 10 times I had more than 51% tails. As a result, 21 times I said the coin wasn't fair, even though it was. In other words, I reached the wrong conclusion in about 4% of the trials. To put this more starkly, let's look at the same thing again, where we conclude a coin is fair if the trial spits out tails between 49 and 51% of the time and unfair otherwise. But this time we'll use a coin that I weighted to be unfair, favoring heads 51 to 49. Interestingly enough, in this set of 500 trials, despite the fact that the coin was weighted, more than half, fully 253 of the trials, fell within my tolerance bounds. So, in other words, sometimes I erroneously concluded that the coin is fair, even when it's not. So that's where statistics come in. In reality, we never do 500 trials, or even 5. The vast majority of the time, we only do 1. So the coin example proves that sometimes we'll get the wrong result. But we only know this because we knew whether the coin was actually fair. In reality, we never know the truth. Otherwise, we wouldn't need to do the study. So when we say that something is statistically significant, that means it is very unlikely that we would get the results we got due to chance alone, even if we've only done a single trial. Evidence of statistical significance in scholarly work will usually appear in tables or figures. I want to spend a couple of minutes walking through how to decipher the types of tables you'll encounter in this class and other social science courses. As you'll see from the caption, this is a study that looks at what happens when a justice needs to recuse him or herself from the case, leaving the Supreme Court with only 8 sitting justices. We wanted to know the conditions under which an even-membered Supreme Court ends up in a tie vote. That's our dependent variable. So in this example, we would say a tie vote equals 1 and anything else equals 0. The table then lists a host of independent variables that we think might matter, like whether or not the United States government through the Solicitor General participates in the case. That's what I mean when I say U.S. case interest. There are other factors like case salience, which is how important the case is, and legal conflict, and other things that we'll look at this semester and go into in much greater detail later. But for now, let's just look at the first independent variable, U.S. case interest. You should see here that the coefficient is negative 0.606 with 2 asterisks behind it. The asterisks mean that there is a statistically significant relationship between the Solicitor General's participation and the dependent variable and the likelihood that the court winds up in a tie. Okay, so that's step one. A systematic relationship exists and it's not due to chance. Note that some of the variables in the model aren't significant, like congressional interest. When an independent variable is not statistically significant, it means that we can't conclude that the relationship between the independent and dependent variables is due to chance. It doesn't mean that there isn't a relationship. It just means that we can't prove it. Step two is to look at the direction of the relationship. Here the coefficient is negative. That means that when the U.S. has an interest in the case, the likelihood that the Supreme Court winds up in a tie vote decreases. So the sign in front of the coefficient will tell you whether or not there's a positive effect, increasing or decreasing the value of the dependent variable. Does that make sense? Then finally, we want to assess the magnitude of the relationship. How much does the Solicitor General's participation decrease the likelihood that the Supreme Court winds up in a tie? Most of the time, academic articles and chapters will provide figures and graphics to show you the size of the impact because these coefficients don't tell us a whole lot. Throughout the semester, I'll show you a lot of graphs when we're talking about impact. In short, statistics are awesome, and they're necessary for both observational and experimental studies because it helps us figure out when there's a relationship between variables and whether or not that relationship is due just to chance. Once we've finally wrapped up our research and published the results, we move on to step 6. Good social science is incremental and iterative. Building knowledge takes a really long time. In order to establish laws of social science, we need replication, which is when multiple studies reach the same conclusion. Like in the coin flip example, the more trials we have, the more confident we are in our conclusion. The tools that we can use are constantly evolving, allowing us to reduce the number of assumptions we have to make. For example, we are always gathering more and different data, and computers are getting faster and faster, and we're getting better at building statistical models, developing fancier measurements. All of those allow us to do better quality work. Additionally, the social world is constantly evolving. Consider how much the context of elections has changed in just the last few years. Social media has exploded and become a prominent part of campaigns. The Supreme Court has shifted the legal landscape on campaign spending, allowing for the creation of super PACs and so forth. With these changes, new questions arise, and we hop right back to the beginning of the process. All right, we have finally reached the end of this very wordy, very dense lecture. Just a quick aside here, there were a lot of words on the screen. I know that. And it's because we're dealing with some really foundational terms and I didn't want you to be scrambling to take notes the entire time. Not all of the lectures will be like this. I just wanted you to have the text at hand for this really basic, really dense material. So it's technical, right? It's a little bit boring. But if you've understood it, if you get it, if you know these basics, the review slide at the end of the lecture should help you assess whether or not you're on track. Take time to review this, go back and review the parts of the lecture where things are still unclear. As always, the discussion board is a tool at your disposal. If you have questions, post on the forum. I'm here to help and I am happy to answer any questions that you might have. Thank you so much for your attention today, and I look forward to talking to you about something far more interesting when we dig into the history of the Supreme Court in the next lecture.